folks, just to kind of show how this was implemented in Python. So the first one we're going to look at is the SimplestSensr, which is this event graph here, and remembering that the parameters is that we have the maximum range and then a mover that's going to model the movement, and then we're going to delegate that, and then just a list of contacts. So this is what we're implementing, and it's in the, if you do a pull on the class code, there's going to be a sensor file, and okay, so we're implementing this. So here are parameters, our max range, and there's our delegate, our mover, and then we just take the arguments, put those into our our variables, our instance variables, and then the other is that we need to be listening ourselves to our mover. So that's what we're going to do here, just so we don't have to do that outside. And then just as is the pattern, like in the constructor, we're going to kind of none this, but in the reset, we're actually going to instantiate it as an array. And so our run is just going to notify the state change for the contacts, which is just going to be this empty contact thing. That's just to kind of make sure things are actually cleared. Now, okay, so here we have the start move to schedule start sensor move, and end move that schedules start sensor end move. And so the start move we're going to hear from our mover, and it's going to schedule a sensor start move immediately because we're moving at the same time as our mover is, and there's the end move. Okay, so now what else is there? Well, there's the detection and the undetection. So let's look at detection. Okay, so detection, we're going to append the target. Okay, the target's the argument. We're going to append it to our contacts. We're going to notify the state change of the contacts. And then we're going to notify state change for the target, and then I think mostly because I was having a little bit of a challenge kind of overriding the toString on this. Let's just sort of have an additional state change for the target location. That's just to verify that when this happens, we're actually detecting the right target. And so the undetection, there's undetection. It just simply removes the target, fire a state change. Oops, this should be undetection. And then the target location for the undetection, just to kind of make sure that's on then. And then here, yeah, we're overriding it with our mover, but we should maybe have that be the current location of the mover. Anyway, okay. So the other thing that we need to implement is this referee. So the referee is going to listen to a mover, it's going to listen to a sensor, and then the sensor is going to listen to it because the referee itself is going to schedule the detections and undetections. That's something that we're going to change in a later implementation. But if you heard the comments in class today, which we're noticing that, okay, if we just have if our referee just we have one for one target and one sensor, then if we have more than one of each of those, we're going to have so if we have n targets and n sensors, we're going to need n squared of these things. And of course, that doesn't scale very well. But we're not worried about that now. We're just worried about getting the thing going. So it's going to listen for start moves and end moves, schedule this schedule range event, which will cancel any pending enter and exit ranges, and then depending on how the routes look, if we have two positive routes, we're going to schedule for the lower one, and if we have one positive route, then we'll schedule an exit range for the upper one. So let's kind of look at that. Okay, so here's our simplest referee. We give it a target, a sensor, and then here we're adding the sim event listener, and we're listening for that, but we also need to do that. Okay, so we're listening to it, it's listening to us. Okay, so here, with all of these kind of weird things, they're all going to schedule this one massive event that's kind of a questionable design, but it's legal. And so each of those is simply going to schedule this one schedule range event. And the first thing we do is we cancel any pending enter and exit range events. And then in a similar manner as I was discussing in class, we're going to put all of those calculations into a helper method called enter exit times. And here, just to kind of see what we're going to notify the state change for that, just to check. And so if there's 1, we will schedule an exit range, and if there are 2, we're going to schedule an enter range. Now, this is a little bit different than in the Java version. We're actually passing ourselves as an argument to this, and that's so that we know how to cancel. We cancel the right one. Notice that when we canceled the enter and exit ranges, we're also passing ourselves in that. That has to do with the fact that the DESpy implementation of the cancel method wasn't as finely implemented as in the Java one. That's the next version will fix that. But for now, this is the correction we need to do. Okay, so our enter range event, this is we're entering range, and this is who we're doing it. And so we're scheduling its detection, and then we calculate the enter and exit times again, and then let's see, if it's 1, schedule the exit, and then we schedule the exit range for the exit time. Okay. And then exit range will simply schedule an undetection, which will be heard by our sensor. And so here's the computation for those enter and exit times. So we get the target location, the target velocity, sensor location, sensor velocity. Why? Because we need the relative location and the relative velocity. And here, here's where, because we could write our little point thing, we added the subtract method to that. And now here we're computing the different elements of this. So this that's the magnitude of the relative location squared, the magnitude of the relative velocity squared, and then the square of the sensor's max range. And then here we're saying, okay, if our velocity is 0, if our relative velocity is 0, then we're just going to return the empty one. Okay, so now we need to compute our determinant. So that's this expression here. And if that's negative, then we have complex roots. If that's positive, and then I think here I have to do. Else if the lower root is bigger than 0. Or what we have to say, what is it, elif? Yeah. Okay. And here we can make this also equal. All right. So let's test that out, and if we look in run, we have a test simplest referee. So how do we test this out? So we have our target location. We create a simplest mover as we've done previously, and we give it a path mover manager, and then do the listening. Now for the sensor, we first create a mover, and then here we're giving it its range. And so here we're instantiating it, giving it the range and the mover, and then we're going to sort of make sure that all that got in. Now here we instantiate our referee with the target and the sensor, and then we're going to listen to the state changes, run it in verbose mode, and if we look carefully at what has happened, we see that okay, we spin through the various run ones. So here's our path mover manager going to the next point. Here's the move to, and then the move to schedules the start move. So now when the start move happens, notice now the referee heard that and scheduled the range, which in turn scheduled an enter range at this 0.8429 time. And notice that our times match what we had done. In other words, this is the numerical example I did in class yesterday. Or was it either yesterday or the day before? I forget. Okay, so here's the enter range. It's going to schedule a detection. And so here we have the contacts, and then there's the location of the target. And then it's going to schedule, then we have the exit range, the undetection. There's the undetection, our contacts are empty, and the target was at that place. Then we finally have the end move. We have a schedule range because the referee heard an end move and said, hey, maybe something's happening. Nothing was happening, and so the event list is empty. And that is the Python one. So if you do a pull on the class code for DESpy, then you will see this and be able to play with that.